here we're going to start up here. Now, you made your airplanes. What we really want you to see is, what I really want you to see, when you flew the airplanes, which plane flew the fastest? The plane with the most amount. What do you think contributes? Let me restate a different question. Do you think wing length? Do you think aspect ratio or horsepower determines which plane flies fastest? Mateo, you jump on. Good job. That way you get here, guys. What is fastest for the airplane? What causes the airplane to go faster? John Mark's got the right answer. Anybody else? Harry, what do you want? Write in an answer what you think it might be. Levi, will raise your hand. I'll take it down and see what you think. Levi, what do you think makes fastest? I'm going to mute you, buddy. I tell you why. All right, let's see what other people said. Yes. So far, everybody's coming in. Airspeed is faster horsepower. Now, but there's trade-offs, which will resort more as lift. But guys, once you have enough lift, that you're off the ground, you're keeping in the air, then you can translate more of the energy you're using into kinetic energy. You don't have to keep connecting it into potential energy, all right, and getting altitude. Now, let's look at this. Range is definitely related to horsepower. As we increase the horsepower in an airplane, we increase performance. We also increase fuel consumption. There's always these darn trade-offs as engineers. Modern piston engines consume 0.5 pounds of fuel for each hour of horsepower. Please calculate the fuel consumption and range of the engines listed below. So, what I'm saying is, let's look at 250 horsepower, and I want you guys to do this for a few moments, all right? Just so we get practice of this. And I will put in this. I'm not really crazy about less than 11. Here, I'm going to drop it over here. Here's an improvement, but I'm even going to improve it better. So you have less than 11 there to add to yours. Okay. So what you think about here is it's saying, okay, I have a range of 360 pounds. Divide that. Now, wait a minute. Mr. Dubik, that says 250 horsepower. But remember, we said 0.5 pounds of fuel for each horsepower. Okay. So we divide that 250 by and a half, basically. So that's saying 125, right? So if you say 365 pounds divided by a burn rate of 125 pounds an hour, all right? All right. So it's 250. So for a half pound of fuel for each horsepower. So if we make it 1-to-1, that makes it being 125. So 360 divided by 125 tells you it goes 2.9 hours. Go do the other 4 right now. Okay? Okay, guys, let me know once you have these, because let's look at the range of this. Guys, I feel like I'm waiting on you. So, give me the calculations here real quick. What do you think that one is? Give me some numbers down here. It's much more fun class if we get some feedback for you all. All right, so let's go to the first one. What do you think? Give me the range for on 150 horsepower. Remember, that would just simply be, see if some minutes there. $4.8 hours. Very good. Yep. Well done. Well done, Harry. 4.8 hours. All right, let's do the next one. It's 200 horsepower. So to get to 4.8, in case you're wondering how he did it, he took half of 150, which is 75. He took 360 divided by 75, and ended up with 4.8 hours. All right, so the next one, it would be 100 divided by 360. So that answer you should be able to do in your head. What's the next one? John Mark, what's the next one? If the first one is 4.8, the next one's got to be 200 divided by 2, or 200 times 0.5, whatever way you want to do it. That means 100 pounds per hour. 360 divided by 100 is what? Yep, 3.6 hours. 250, it's 2.9 hours. You can see this value slowly going down. 300 divided by 360. Is 1.2 hours. Right? And then finally, the last one. Oh, wait a minute. I might have just messed up. Excuse me. Wait, I jumped the gun. 360. Sorry, divided by 150. That's not. 2.4 hours. I jumped the gun. 2.4. And then the last one is going to be 2.0. So 2.0 something. So you're slowly going from 4.8 to 2 hours. So you as an engineer have this trade-off. If you want a range, you're only in the air 2 hours. Wow, you really can't go as far because you got to stop and keep getting gas. Well, now we've got to add more weight, make the airplane bigger, because you got to have fuel tanks. Fuel tanks are in the wings. So you have that going on. The plane's now bigger. It's now getting more expensive. It's probably going to have higher wing loading. You're going to have to make it sturdier. So that's why there's all this trade-off. That's why you see airplane, when you start getting to, say, 1,000 horsepower, you have a really expensive airplane. And it's not just because you made an expensive engine. It's because everything else to support that engine. You need more fuel. You need a beefier structure. You need everything. That's why smaller horsepower, hey, the big trade-off in engineering is if you make them just as strong, but make it lighter. Because really what you're doing to get lift, to get this thing moving over, you're using thrust to overcome drag. And I imagine original inertia. You're really getting over the drag of the airplane, the weight of the airplane in the beginning. And that inertia that's there. But so if you things make lighter and cleaner, you can both save fuel, and then the trade-off gets to be, okay, we can either make it go farther or we can make it go faster. You probably can't do, or you make it cheaper, but you can't do all three. It's kind of like you can want it fast, you can want it well-built, you can want it inexpensive. You don't get to do all three. If you want it fast and well-built, it's expensive. Now in an airplane, what I'm saying is, if you want to go fast, you want to go far, it won't be a cheap airplane. If you want a cheap airplane, you can make it go fast, but it's not going to go far, or it's going to go far, but it's not going to go very fast. Depends what you're doing in the airplane, too, what you're designing for. I'm looking into flying some ultralights. You fly that, you're just cutting holes in the air. You're not flying an ultralight across the country. All right? You can go across the country faster than a motorcycle or something. All right, so now, and see, and this is what it means. Again, as you learn, increasing the horsepower means improved performance at a cost of greater fuel consumption, which, by the way, cost of operating, and fewer people can buy your airplane. Higher airplane performance typically means higher wing loading. Higher wing loading means longer runways and higher stall speeds. So you got to be a better pilot to fly. You got to have better runways. You can all these trade-offs as you're an engineer, you start thinking about it. All right, so let's go to. I'm going to go to this. Pull this back up. Let's go to the next lesson. We're going to go into airplane design. And with Tom, you're going to start going over some of these down the road. So we even go into greater depth. Some lessons you've never seen before. But let's go here. Because remember, too, you learned there's not a direct relationship between speed on the plane and how much horsepower either. Wish there was. All right. Now, if you have never downloaded, it's a good time to do it. But, this was originally when we designed Fly Learn, I wrote this curriculum, was to get you to really learn the engineering method more than planes. Since then, everybody's got STEM projects and they all have them, but ours is really the STEM process. All right? So research, prototype, planning new aircraft. And what you need to do, and we iterate, and we're going to keep going this over and over this. Now this kind of pops down here. I don't know why I did that, but did that. All right, so here we're going to go. So we've done enough type of engineering things. You know what you're going to do is you're going to design something, build it, test it, repeat over and over again. Okay? Prototype, a few steps that are done many, many times. You just keep iterating until it gets better and better. Build a new prototype, test the prototype, make a change, do it again. I'm doing that very thing right now. All right? I'm building a box control panel. That's throttle. I've already made 2. We're making 3 changes now. All right. All right. So, if you would, either bring this on an iPad, but let's start working on this together as we go through this, all right? So let me give you a minute. Go get something, either write down or start figuring this out with. You're going to get a lot more out of this if you work on it. And then some of this is your design. It's not going to be my call. Levi's got a question. Do you have a question, Levi? Write it down there for me. All right. All right, great. Now, let's go ahead. So here's the first thing you start doing on this. All right. When you're designing your airplanes, there's certain specs. Here's the thing about engineering. I think this is important to understand. A lot of times you get the airplane performance design specifications. Where do you think you get those from? Is it something you come up with, or where do you think it comes from, folks? Where do you think it comes from, everybody? Folks, you're making me sad as if you're not listening to me. I'm being sarcastic there, but seriously, where do you think it comes up with? Any ideas? Who dictates, hey, how about future customers? How about research? So it's your department. When you start a business, you have to bring something to the market. All right? So if you're starting a business to build airplanes, you should probably know what your customer wants in their airplanes. True? That's what you want here. What do they know in this? So in this case, people are saying, not surprisingly, a 4-passenger airplane. You can take your spouse and 2 friends. Now, honestly, most 4-passenger airplanes, in my opinion, you can take your spouse, your spouse, and some luggage, and that's it. If you take friends, there's really not much luggage going along. Each passenger can carry a bag of 20 pounds of luggage. So we're making this a bigger one. So this is not a Cessna 172. This is going to be a starter one. Notice 20 pounds isn't a lot. You got 150 knot cruise speed. You would love to see an 800 nautical mile range. All right? Now, that nautical mile range is pretty beefy. Okay. So let's mathematically model your airplane. The average passenger weight is 170 pounds. How much luggage will they each carry? We said 20 pounds there. How much the average weight per passenger there is? Well, okay. Let's think about this. As an average idea, we can sit there and say that's about 200 pounds, all right? Well, wait a minute. Your average passenger weighs 170. I should say the average weight per passenger per luggage, 20 to, I don't know how I jumped a step there. 170 plus 20, that makes 190. How many will we be carrying? 4. So total payload is number of passenger times that average weight. So that's 170 plus 20 is 190 times 4, 190 times 4. And that's going to be like 760, isn't it? I don't know. Let me check. Yeah, 760. So you have 76, all right? Does that make sense so far? Then, modern aircraft designers have learned through past experience that airplane weight can be determined by doubling the total payload weight by 30% or 0.3. You know, rule of thumb. So they've done enough airplanes. They say, okay, so if I take my gross airplane weight, which I just said was 760 pounds, divided by 30% to get the gross airplane weight. So if I have 760 divided by 0.3, I get 2,500 pounds. Hey, by the way, not surprisingly, that's what modern planes are doing. Just the one you just did. Okay, so right there, we have that. Now, wings, now we need to calculate the size of wings for airplane. We'll figure out the wing loading, determine wing area, aspect ratio, and finally wing span. All right. And so what you do on this is you take your gross weight that you just previously calculated, you put that, all right, take the square root of that, minus 6 times 2.4 to give the standard wing loading. If you want high wing loading, because that's what your plane's going to be, you multiply by 1.3. If you want low wing loading, do it by 0.7. All right, folks, I'm going to let you pick some of this out. I'm not going to work through each one. I want you to spend a few minutes here. It's 8:30. We'll spend 15, 20 minutes letting you work on this. Then you take that gross airplane weight again, which you previously calculated, the wing load range, whether you use standard, high, or low, whatever you decided. Remember, high wing load, higher performance, can carry weight, but you now need longer takeoff distances. You have a higher stall speed, so it's a little bit harder to fly. Probably going to be using more fuel. Then all right, then you take that wing area, that's the gross airplane weight, divided by the wing loading, all right, to get our wing area. Remember, wing area is chord by wingspan. So you can sit there and go, okay, so 6 to 8. So use a 7 as an aspect ratio. So 7 is that. Wing area is previously calculated. Then you can figure out the wing area of that. Then wingspan, B, equals S, wing area, previously calculated, times aspect ratio of 7. Take the square root of that. All right, and that'll give you a scan, and then you can figure out chord. All right. Okay, guys, can we take a few minutes to sit and calculate this, please? All right. Yeah, Mateo, what's your question, buddy? Hello. I'm right here. I want you to work your way through it, guys. I used to ask kids to do this outside of class, but it became real apparent to me that they didn't have time. So that's why we take class time. I'd rather you go through this and understand it. All right, let's see. And that actually should be a 550 nautical mile range. There's no way you do 800 on that. Not missing anything. We're just working on this right now. Let's keep working on it. We'll go through it together in a little bit. Are there any questions on it? Let me go through this again. I see there might be. Just making sure you didn't miss anything you didn't. Come on, let's work through it, guys. It shouldn't take us all that long. Yeah, your wing loading is doing something wrong. Okay. All right. Remember, you're taking the gross. Let me go back to my PDF there. So remember, your weight of your airplane, gross weight of your airplane is 2,533 pounds, 12,533 pounds. So standard wing loading is something equivalent of basically 2.24 times parentheses. Think of it this way. Did I say 2? I mean, it's actually, it would, all right, the gross weight, let me do my number here. So let's do this. It's the gross weight, square of the gross weight minus 6. So let me go on mine. See if I have this, I don't have, let me see if I can get enough function. Oh, let me get an online calculator here. My phone is useless. There we go. All right. There it is. So, I'm sorry, I'm sitting here just trying to, my goodness gracious. Lots of bosom. All right. Bear with me. Let's try this again. I should have done. I believe this should be the key. I may have, let's try that. Go back to my thing. Okay, it's the cube root of the weight. Let's try that again. Times 2.24. So let's do that again. That's what I said the weight was. 2533 on mine. I'm going to go back. Three. All right. Hang on. mine ended up, my standard wing loading was 17 pounds per square foot. That should say, this isn't really clear, it's a terrible screen. Let me give you a better version of this. What is that? Gamma Learn to Fly student curriculum. See if that's the same one. Pull it up over here. This isn't clear. That's a cube. That's not a square. It almost looks like 2 here. It's the cube root of the gross airplane weight. I went back on a better looking view of this. That is a cube, gross airplane weight minus 6. All right? So you're going to come up with an answer. You're going to end up with about 17 pounds per square foot. Did that help, John Mark? And then take that 17 pounds per square foot, multiply it by 1.2, you're going to get 20.4 or 13.6. All right, guys, can we all sit and go through this? I'm a little bit concerned that I've got no other questions, only John Mark that had that question. So hopefully, you know, I hope we're not all playing, never can think of the name of that game. Look it up right now. All right, so let's go back here now. Let's go through this. All right, so you calculate, this is 2533. If you take the cube root of 2533, you're going to get a value, minus that by 6, multiply 2.24, you end up with 17 pounds. If you make it high wing loading, you're going to increase that by 1.3. That's 20.4 pounds. And if low wing loading, it's 13.6. Any questions on that? Any question on that? Then take that gross airplane weight you did before, 2533 again. The wing loading before, I'm just going to keep mine general. Yours will change based on this, but if I just stayed standard wing loading is 17 pounds per square foot. Now wing area is the gross airplane weight divided by wing loading. And that should make sense. When you do that, look at your units. You have gross airplane weight is, what do we say, 2533. You're dividing that by 17 pounds, so the pounds cancel off, and the square foot goes in the denominator. So you end up with an answer of 149 square feet. Now, if you use a higher wing loading or winger loading, the value will be different. Does that make sense? Any questions so far? Then you've got your aspect ratio. Your aspect ratio in this case is going to be 7, because it's between 6 or 8, so we use 7. We just give that to you. The wing area previously calculated was 149 square feet. So you take the wingspan, which is known as B, equals the wing area, which is S, times the aspect ratio. Take the square root of that number. All right? So if my wing area from the past time, let me do my calculations here, is 149 times 7 is 1,043. Square root of that is 32 feet. I'll make sure of that. So I'm going to go here. Yep. It's 32 feet. Then take the chord, which is the surface area, which is the wingspan, divided by B, the chord. That would give you that. So let's, excuse me, let me back that up. I almost blew it. Wing area is S, wingspan is B. So S divided by B, so in other words, the wing area, 149, divided by the wingspan, 32, will give you a chord of 4.6 feet. All right. Now, any questions at that point? Has everybody got it there? All right. Any questions, guys? Feel like, all right. Now, Trey, let's assume you need 150 horsepower to get this airplane, the power to create drag times velocity. The calculations determine power beyond the scope of those lots. Let's just assume you need 150 horsepower, right? This is called brake horsepower. Modern propeller is 80% efficient, converting brake horsepower into actual thrust. So I take brake horsepower, 150, divide it by 80, I get thrust horsepower. So what would that answer be? Well, 187 brake horsepower is basically what you need is 187 to get that horsepower. Then to get thrust horsepower, you just calculate 187, divide that by 75%. So you're going to end up with 250 horsepower here. Again, you need 150, but because the propeller is not completely efficient, and because it's not a good idea to run an engine at full thrust, you've gone to 250 horse. All right? Now, what you can start to do here, as we're about over time here, you're going to get to this point right here on range. All right? That's the gross airplane weight, which you calculated earlier, total of fuel available. That's equal to gross airplane weight times 15% to get how much you need. So if you take the gross airplane weight, which is 2533, multiplied by 15%, you get 380 pounds. Payload weight is what we figured at the very beginning, 760 pounds. People in it, 20 pounds of luggage. That ends up to an, all right? So to get your empty weight is your gross airplane minus your total fuel available and payload weight. So WG minus WF plus WP. In this case, that'd be 1,393 pounds. Cruise speed is 150 knots. Your fuel consumption is 0.5 pounds per horsepower. You would see it, you'd have a range of 608 nautical miles. So then you could start playing with this to say, well, I want a little bit faster airplane. Well, as long as you stay, above that 550, you could do that. But you would get less gas mileage. So it's always a trade-off there. All right, everybody? It's always a trade-off there. And for some reason, I have a very funky issue here. I got to figure out why my... I have two... this is the same as the other one, so I'm going to fix that out over the week here. Figure out when the world's going on. Okay? So, any questions of what we just did? Now, just so you know, before you hang out, Thursday night we have a lab, building foam airplanes. Saturday we have a lab, building foam airplanes. If you took a foam airplane home with you Saturday, make sure you bring it back. So that's what we got going on. That's what we have going on this week. Remember, we have a lab this week. Any other questions? Okay. You're going to go into doing some other lab work. We're going to keep... Once you build this plane with these dimensions, and then you can actually go on, and if you go on the next page, you get your values, put them in your airplane, and fly it. All right? And then you can start adding thrust to see how much faster your airplane is. Go ahead and designing a 2-passenger with a pilot, 250 thrust horsepower, and aspect ratio between 6 and 8. And that way you'll make it. Okay? Any questions? Okay, if you didn't have any questions, that's all I've got for tonight. Good night, all.